introduction. Thanks a lot, Francois. Thank you again to the organizers, and thank you everyone for attending and participating. So again, feel free to ask questions in the chat, and I will be happy to answer, or otherwise later by email as well. Any question or comment, please feel free to contact me. So indeed, this sixth and last lecture will be about reinforcement learning methods. So let me just sketch the outline. I will introduce a bit the topic, and then I will discuss reinforcement learning for mean-field control, for mean-field game. I will have one section about a framework, which is an open source framework, which already contains quite a few environments and methods to solve mean-field games using learning algorithms. And hopefully there will be more and more. And if you're interested in contributing, that would be great. So feel free to take a look. And then I will.
There is one question, by the way.
Yes, there is one question.
There is one question before we start.
Thank you. So before we start, so someone in the chat says, I have a question. In the part 3, master Bellman PD for MFC, instead of finding the value function v that depends on the distribution mu, the algorithm will find a symmetric function vn that approximates v when n is big enough. Yes, so maybe I can go back to this slide. And actually it's good because I was about, I also wanted to make some comments. So it is on this part. And let me jump directly to the location where you have your question, which is probably the slide just before. So this one. Okay. And the question is, if I have tx and mu t, how can I calculate v of tx and mu t using this vn function? Yeah, that's a very good point. Thank you. So here the idea was to approximate the function v by a function vn, which will be encoded. It will be encoded as a neural network as a function of, in fact, this one, all the x's here. And the question is, well, if I want to evaluate v as another point, at another distribution, how can I do that? So what you can do is you can sample n points. So you can sample xi according to mu independently. You get n samples, and then you plug these xi's here in your neural network. And because the neural network is symmetric with respect to the input, the order doesn't matter by construction. So I hope this clarifies how to use this neural network afterwards. But indeed, the size of the population is fixed. So if you want to use a larger population, you have to retrain the neural network, which is a drawback of, well, it's a limitation of this approach, but this is how it is constructed, at least as I explain it here. So I hope this answers the question. Since we are here, I had a few other questions at the end of the previous lecture, so thanks a lot for your questions. Let me stress that I added a few references, so I updated the slides. I keep updating the slides. I will probably update them again at the end of the lectures to correct just a few typos and add a few references. So please feel free to take another look later. But here, yeah, okay, here I added, whoops, here, sorry, I added a reference to PINNs, physics informed neural networks. So yesterday, I think Abdu mentioned this, and I didn't discuss PINNs here, but there is a broad literature now on this type of neural networks, which also solve PDEs. So there are other approaches to solve PDEs than the DGM method I described here. I also added a reference here to a paper of Reisinger and co-authors, where they use, in fact, they try to solve a PDE system for mean-field control, but with faster convergence than the DGM method I have presented here. Furthermore, I have added also some references in this slide deck. So at the end of the previous lecture, someone asked about kernel-based methods. So here I added what I had in mind. I don't know if it answers your question, but there are some other papers. As far as I know, there is not a very long trend of papers on this topic, but probably more than just the 3 I'm citing here. So There is probably more in the literature. Kernel-based representations, this one for the mean-field interactions, Fourier approximation. And I know that Francois also has a recent paper using Fourier techniques with Alekos check-in and Gaussian processes here. But this one that I'm citing is really numerical, I mean, driven by numerical motivations. So there are other approaches in the literature particularly to encode the mean-field interactions. Okay, so let's see. Okay, thank you for your feedback. So let's go back to this slide deck. And okay, related to references, feel free to let me know. I apologize, it's not really possible to be exhaustive, and I certainly am not aware of all references. So if you want to bring to my attention some references, feel free to contact me and to let me know either in the chat or later by email. So in all the previous lectures, in some way or another, the numerical method was using the full knowledge of the model. So in the ODE, PDE, FBSD, it was somewhat clear because just to write the PDE or write the FBSD, we had to know the model. We had to know the drift, the cost function, as well as the boundary conditions, etc. So we use the model in the so-called direct approach, what I call direct approach in lecture 4, actually. Yes, in lecture 4. The direct approach, basically, you parameterize the control, you compute the cost, and then you make a gradient step. So you could say, I just need to see the cost. I don't really need to see how it is computed. So this is true, indeed. You just need to see the loss and you try to tune the control. However, when you do this gradient step, you compute the gradient of J theta. And to compute this gradient, you need to have the exact expression of J, at least if you compute this gradient exactly, right? So part of the reinforcement learning methods, some of them will be about approximating this gradient without knowing really the model. So without differentiating through the drift, differentiating through the running cost, and just using estimates of the gradients based on observations of the cost. This will be related to the policy gradient methods that I will describe a bit later. More generally, the motivation for model-free reinforcement learning is twofold. We say model-free, so we can say these methods are useful when we don't know the model. Yes, that can be one motivation. Sometimes maybe you interact with nature and you don't want to make an assumption on how nature works. You just want to try to take some actions and see what gives you the best reward. I'm usually going to talk about reward in this lecture instead of cost to match the literature and reinforcement learning. But another motivation to say maybe I know the model, but just the model is extremely complex, maybe in extremely high dimension, and then I cannot use, or it's not efficient to use exact methods as I have described before. For example, if your model is so complicated that the PDE will be extremely difficult to solve, maybe you don't actually need to solve the full PDE. So this is connected to also a question Abdu asked at the end of the last lecture, the connection with finite population games. And my remark was, maybe FBSDs make more sense than the PDE because at least they're going to solve along the trajectories that really matter. Ideally, they're going to train the neural network on trajectories that really matter. And in fact, this is really a key point in reinforcement learning. You learn, and along the way, you explore the path, the state space in the regions that matter, because you know that you will not be able to explore the whole space, but you don't need that to be approximately optimal. You don't need to explore the whole space. You just want to explore the regions that matter. So I will not discuss too much the trade-off of exploration and exploitation, but this is an important aspect in reinforcement learning. But I will discuss this question of sampling at some point. Okay, so sometimes we know the model, but it can still be interesting to use reinforcement learning. In the past few years, probably you've heard about some successes of reinforcement learning. I would say even deep reinforcement learning, combining RL with deep neural networks. In particular, the game of Go received a lot of attention. Recently, the game of Stratego, which is a game where you don't have full information, so it's more complicated than Go, and there are many other improvements. Reinforcement learning is also involved in ChatGPT. You have probably heard of ChatGPT, so reinforcement learning is also involved there. So really a lot of applications and success stories. Here, why could we be interested in mixing that with meaningful games? I would say from the computational point of view, again, this is about numerical methods. Maybe you could also discuss the interpretation of reinforcement learning. So an agent learning, maybe this is realistic because you are trying to understand what happens when people learn. So that can be a motivation, but here my motivation is really computational. And so I would say there are two aspects. The mean field approximation allows us to scale in terms of population size, and reinforcement learning hopefully helps us to scale in terms of environment complexity. This was already the goal with deep learning methods I described before, but here maybe we can go even further because we try to get rid of the dependence on the model. So there is a connection with multi-agent or maybe many agent reinforcement learning. So multi-agent reinforcement learning is MARL. And in some sense, there will be connections, but as usual, using the mean field game paradigm, we are not going to model different agents. We are going to focus on one representative agent learning while facing the population and how the population adjusts. So the reinforcement learning setup is typically described in this MDP formalism, Markov decision process. So you have a state space, an action space, a transition kernel, which can be given by a transition function plus some noise. I will often use this example, a reward function, and you care about the total reward associated to a policy. And the goal is to maximize the reward, which is equivalent to minimizing a cost. Here, I will take most often, not always, the infinite horizon discounted setting. At least that's the most common one in standard reinforcement learning. But in mean field games, it's not the only interesting setting. I think the finite horizon setting is also very relevant. I will come back to this later. Okay, and here you see that I allow randomized actions. So you sample action AN according to the distribution pi of Sn. And notice that pi is stationary thanks to this infinite horizon discounted structure and the fact that the reward is stationary. So one of the difficulties when we look at the mean field game is if suddenly you plug the distribution at the current time step, mu n, and then you look at this reward function from the point of view of the agent, it looks like this, then, well, this is actually time dependent, right? So it is not stationary anymore. So if the population moves, then your reward function as a function of your state and your action is going to change. This is not only in mean field game, it's just in games in general. And so this creates some difficulty because the environment is not stationary, and then it's not sufficient in general to look for a stationary policy. Okay, but here I'm anticipating a little bit. So the model is P and R, basically, and gamma as well. And if you know everything, if you know P and R and gamma, so if you know all of this, then you can use exact dynamic programming. You can write the Bellman equation as I did in the first lecture. So here you can see lecture 1. That's why I wrote this value function and I wrote the Bellman equation. So you can do that and you can do a backward iteration, which is basically like solving a fixed point problem in this stationary regime. If you don't know the model or if you don't want to use it, then this is what is studied, in the mean field game framework. So the idea is the following. You are one agent, or you implement an agent trying to learn the optimal policy by doing experiments of the following form. So the agent chooses an action, observes the state, ST, which could be his own state or the state of the system, takes an action, gives this to the environment, some kind of simulator, let's say, or a black box, and the simulator returns the new state and the reward obtained by taking this action in this state. But you don't know how they are computed, right? So basically, you have a picture like this, and ST+1 is distributed according to P of ST and AT, and you know that, I mean, the reward will be given by some function R of ST and AT, but the point is you don't know these functions P and R. So you just use samples and you try to learn the optimal behavior. Here I refer to the book of Sutton and Bartow for more information. So there are several classical algorithms. One of them is policy gradient. So the idea is you look at J. So here for me, J is equal to minus R, minus the reward. So I want to minimize J, or I want to maximize the reward. And I can do gradient descent, provided I know J. If I know J, I can compute this gradient exactly, or maybe I can do a stochastic gradient descent version. But in general, we don't know J, so we have to do some approximation. There are many variants, PPO, TRPO. Another approach is to try to learn the Q function, which is a variant of the V function. So the V function is a function of the state only, and it is the sum of the future cost or rewards. And the Q function is the first reward because you fix the action. So you are at a state, you say which action you want to take immediately, so you get a reward. And after that, you follow a policy or you play optimally. So the main advantage of having this Q function is that the V star function can be recovered easily by taking the best action. So the best action is the one that will give you the maximum Q value. And you can also recover the optimal control by just taking the argmax. Again, it's possible that you have multiple optimal actions. For standard RL, it's not an issue because you are just looking for one optimal policy. But in min-field game, it might be an issue if you have ambiguity about if you have multiple best actions. It's not really clear how you should distribute the probability to pick these actions. And there are extensions using DeepQ network, DQN for short. So I will not go into the details, but there are references in the literature. I will show just briefly some of these algorithms next. And there are some hybrid versions. Sorry. DDPG, deterministic policy gradient, soft actor critique, SAC, in which you try to learn at the same time a policy and a value function. All right. So here is taxonomy borrowed from the website of OpenAI. So RL algorithms, there is a whole part on model-based RL that I'm going to skip. I'm going to focus on model-free RL. And you see the distinction between optimizing the policy, learning the Q function, and you have some methods at the intersection because you learn in parallel the policy and the value function. And you have versions that are tabular, that are parameterized using some fixed set of features, and some versions that are fully deep learning. So they really combine, for example, this one has a D inside, DDPG, and it's really using deep neural networks for the policy and for the Q function. So it's a combination of deep learning and model-free reinforcement learning. So here is the algorithm for DQN. I'm going to skip that, but you can take a look. The algorithm for DDPG and the algorithm for SAC. Actually, I'm going to present later on numerical experiments that use some of these methods, right? So that's why I just wanted to provide the algorithm. And these are screenshots from the paper. So you can find the references here. So what is the setting for, how can we adapt this setting for min-field games and min-field control? Well, of course, the main point will be to handle the distribution, right? And the interaction with the distribution. In a mean-field game, the bottom line will be that we are going to use reinforcement learning for a representative agent facing the distribution. So the distribution will be somehow part of the environment because it will be involved in how you compute the reward and maybe how you compute the transition kernel, but it will not really be necessary for the agent to observe it if we follow the strategy of looking for decentralized policies, right? Remember, that's one of the advantages of mean-field games, at least without common noise, etc., the plain standard mean-field games. It's enough to look for decentralized policies. So if we use that, then the agent needs only the observation of his own state and not of the full population. On the other hand, if we take the point of view of MFC for a central planner, then the value function is a function of the distribution. And in principle, you are going, if you want to compute this Q function, the Q function will be a function of the distribution. And so we are going to assume that you observe this distribution mu. It's also in the environment, in the transition and in the reward, but you observe it and then you take an action. This action here is not the same as this one. The one on the left is for a single agent. The one on the right is for the whole population. So basically it will be a decentralized control so that all the agents can decide how to move forward based on their own state. So I will explain this in detail, but this is at a high level, at least one way to adapt this reinforcement learning setting to the mean field case. One important question is the distribution approximation. Even if mu is only in your simulator, you see in the case on the left for mean field game is just part of your simulator, part of the environment. But still, you need to store that in your computer, and you need to update it, and you need to put it in the reward and in the transition kernel. So just to be clear, the environment is something that you implement. You also implement the agent who is learning, but the agent does not see the inner working of the environment, right? So you implement everything as a programmer, but the idea is that the algorithm, the learning algorithm, the reinforcement learning algorithm does not know what is happening in the environment, right? So it's more a question of point of view than really that we don't know the environment. Okay, so there are several ways. Most of the literature, at least on RL for MFGs, focuses on the finite state space model. But for example, with Sarah Perrin, we worked on using normalizing flows, which is a kind of neural network to capture the density, to represent the density in a continuous space model. Again, if we are not talking about RL, there are several papers that discuss approximation of the density. So I cited some of them just in the previous lecture. And we could combine, of course, these ideas with reinforcement learning. So before going into some of the details, here is a non-exhaustive list. So as you can see, the list is already pretty long, and I'm sure it's not complete. This is for mean-field game, for mean-field control. Here is a partial list, and the list is growing very quickly. Some of the talks are available on this website. So we are running a webinar where some of these papers have been presented. In particular, so François Delarue gave a talk, as well as Singuo, and recently Tamer Bashar and several other people. Like the last one, for example, was I think our most recent speaker for model-based reinforcement learning. And there is a survey on this topic with an updated version coming soon. So if you have comments or remarks, missing references, etc., feel free to reach out, and we will be very happy to include that in the survey. I will focus on mostly on the dynamic setting, what I call the dynamic setting, in which the distribution can evolve. I will discuss the infinite horizon setting, the finite horizon setting. It doesn't make such a big difference because anyway, the distribution evolves, which means you cannot be satisfied with stationary policies. So there are other settings, for example, the static one. So here I would refer to lecture 1. The stationary setting is a setting in which the distribution is stationary. So it is at equilibrium because it's a Nash equilibrium, but it is at equilibrium from the point of view of the dynamics. And as an agent, you try to find your best policy. So the agent is going to move around, maybe, but overall, the population is stationary. And here for today, I will mostly focus on the evolutive setting in which the distribution changes over time, because it's more interesting for applications. So RL for mean field control, and I will also call that mean field RL in the sense it is reinforcement learning with a mean field state, because the state becomes the population distribution. And I would like to stress that for mean field game, the situation will be different. We are going to have a meta algorithm to update the distribution, for example, fixed point, for example, fictitious play. And inside these meta iterations, we are going to have a subroutine doing reinforcement learning to train the policy. But this will be at the level of a single agent, so it will be standard reinforcement learning somehow. So the difficulties are different. In the mean field reinforcement learning setting, the difficulty is that you have some very high dimensional or infinite dimensional state, and you want to do reinforcement learning. In the other one, maybe the state is finite dimensional because it's for a single agent, but you have to alternate the population and the agent. So what I would like to do in this section for mean field control is to describe the setting, describe the policy gradient method, and then the Q-learning method. So you see learning the policy, learning the Q function, and of course, then you can play a lot with that. And I will provide one code which uses DDPG, so the deep deterministic policy gradient. This is again, so just in a nutshell, if you take one step back, from optimal control, you can go to mean field control, which is what I did basically in the first lecture, right? You can also go to reinforcement learning by saying, I don't know the model, or I don't want to use it in my numerical method. This is typically for a single agent or a finite dimensional system. And then if you combine the two, you would get what I want to call here mean field reinforcement learning. So maybe it's just a mathematical abstraction. Is it useful in practice? Well, I would say if you have a system with a finite number of cooperative agents, for example, drones or robots, and they are trying to learn, basically what you could tell them is, instead of trying to solve your n agent problem, try to solve the mean field problem, because it will be simpler. It's an approximation, but it will be simpler. You learn decentralized policies. You focus on this mean field term, assuming you are really in the mean field limit. And then once you have this policy for the mean field problem, you can plug it back in any situation with m agents. In fact, m does not have to be equal to n, and you will be approximately optimal. So you lose some epsilons, because in real life, you have a finite population. When you are learning, you don't have a mean field population. So there is an approximation. Then you take the policy you have learned and you apply it in a finite system. So you lose another epsilon. But in some situations, you can quantify these epsilons. So here I will take as the following setting. So I assume that the state evolves according to a function f, which is a function of the current state, the action taken by the agent, the mean field term, some idiosyncratic noise just for the representative agent, and some common noise. So the common noise is the same for everyone. And as a consequence, mu n is the conditional state action distribution. So here I should say conditioned on the realization of epsilon 0. You can think of some aggregate shock, which is shifting the whole population. So if you want to know the state of the population at the current time, basically you need to know the history of past shocks. Pi n is a randomized policy. So this is a randomized policy for the agent, meaning the representative agent has a distribution over actions and sample from this. In fact, it can also be interesting, at least from the theoretical point of view, to allow the policy itself to be randomized. So there can be two levels of randomization, but here I will focus on randomization at the agent level. So you sample from pi n. The cost is a function of pi and mu. So here I'm putting the two because I want to have one cost function and then I can use it for mean field control and for mean field game. So if I go to the next slide, based on this setting, I can define mean field control, where I look at j of pi and mu pi. So if you remember the first and second lectures, this means that really you have a function just of pi. Actually, it's what is written on the left. You have a function of pi which controls the population. On the other hand, if you want to do a mean field game, you split this into two steps. Given mu hat, you optimize over pi, and then given pi hat, you look for the corresponding population distribution. Here, this should be a pi hat. The process is controlled by pi hat, and P0 means I take the conditional distribution. So this here, this means a conditional distribution of x given epsilon 0. And here, same thing, it should be, well, actually, okay, it can be alpha, but anyway, I will put a pi to be consistent. In this section, I focus on the mean field control, and in the next section, I will go back to the non-cooperative mean field game setting. So thank you. There is a question. How do you interpret the discount factor gamma in this case? It's a good point. So here, the way I interpret at a high level, let's say, but this is maybe standard, but the way I interpret the factor gamma is that it controls the preference for the current time. So if you put a very strong, if you put gamma, so gamma is between 0 and 1. If gamma is very close to 0, gamma to the power n is going to decay very quickly, meaning that you care almost only about the time steps close to 0 at the beginning. And then after that, you don't care about what happens, meaning that maybe your actions will have very bad consequences, but you discount that. Maybe f is going to become huge in the future time step, but you discount that, so you don't care. You don't care about the consequences of your actions. If gamma is large, meaning close to 1, then you care about the consequences of your actions for a very long time, and so it's harder. So typically taking gamma closer to 1 makes the problem harder than gamma close to 0 numerically. So that's a good thing to have in mind if you want to test a method. Test it with a small gamma first to see if it works, and then try to increase gamma. All right, so I'm not going to discuss too much the theory, but I want to explain the idea about how to design numerical methods. So one of these numerical methods, actually the second one, is based on the Q function, which satisfies the dynamic programming principle. I briefly mentioned the dynamic programming principle in the continuous time case. What happens in this discrete time setting? So actually, we can do the same thing. We can develop a dynamic programming principle for the value function. And the key remark to do that is to note that x will not be enough as a state. We need to look at the population distribution as a state. So this expectation here, I mean, this is the original formulation of the cost. By the way, here I'm using the notation alpha. I'm kind of mixing alpha and pi, but actually, what I mean by that, this is because I skipped some details, but what I mean by that is that alpha here is a process. So alpha is a process, and pi is somehow the distribution or the conditional distribution given the state at each time step. So it's not wrong to say that that x depends on alpha and that mu depends on pi, because mu depends only on the law of the control process and not really on the process itself. But you can put alpha or pi everywhere. So the first remark is to say, I don't need this capital X. I don't need capital X because capital X is involved only through an expectation. So I rewrite the cost as an integral over the action space, the state and action space. So this should be A. Note that I still have an expectation here because of the common noise. So I cannot know exactly the evolution of the distribution, but if you give me the distribution at time n, the state action distribution, then I integrate it and I get the cost for the population. So this is the population cost at time n, paid by the whole population, the mean field population. Right? But the thing is that this distribution is stochastic because of the presence of the common noise. So I need to have this expectation outside. Nevertheless, this looks very much like an MDP, but now the state is the distribution, the state action distribution actually, and it is stochastic because of the common noise. So it is really an MDP. If there is no common noise, then we don't really need to talk about an MDP because the evolution of the distribution is deterministic, right? Okay, so the state is a population distribution. The value function will be a function of the distribution. So the formalism is a little bit abstract, maybe, at least the one we proposed with René Carmona and Zhong Juntai. So the idea is the state space here, there is no surprise. It is a state, it is a space of probability distributions. But the action space is the set of probability distributions on S times U. And U is like A, if you want, it's like the action space. So in this case, you can write the evolution for the distribution, which is just pushing forward using the function capital F, and you can write a reward function or a cost function for the whole population distribution. Here, I put a minus because I want to have a reward function to fit with the literature on reinforcement learning, which is usually for MDPs with reward functions. So in this way, you get a new problem, which is written here. And this is really the mean field MDP that I was mentioning before, where you start from a state mu. This is your initial state, and then it is going to evolve. You control it through pi bar, so you can control it, but it evolves in a stochastic way due to the common noise. And at each time step, you get a reward R bar, which is for the whole population, right? And you want to optimize this. You want to maximize this now. Okay, so based on this, you can write and prove a dynamic programming principle. In fact, it's more or less a standard MDP, except the state is a bit strange, and the action space is also a bit strange, because you choose a policy, and then the agents at the lower level implement this policy to sample their actions. So the formulation of the MDP is a bit complicated, and you cannot apply directly, immediately existing results, but you can really apply results indirectly somehow after reduction. So the dynamic programming principle tells you that the optimal value function starting from a state mu is equal to the first reward plus gamma times the optimal value function at the next time step. And this is integrated with respect to pi bar because you have different actions. So you integrate over the set of possible actions. The proof, I'm not going to describe it, but it's based on results of Vertsekas and Shreve. So they have a book on Markov decision processes or optimal control in discrete time. And then there are, I mentioned here, there are already mentioned it before, there are several results on dynamic programming for mean-field control, including in a very similar setting by Gu et al. And Singo and co-authors. In their case, they didn't have common noise. So I think that's one difference with what I'm presenting here. And Mott and Pham have common noise, but they focus mostly on open loops. And also another difference is that they don't consider the double randomization. So randomization at the agent level and randomization at the population level, which turns out to be important in our case. And I think the randomization at the population level is also meaningful for reinforcement learning. So discrete time infinite horizon, common noise, feedback controls. So this seems very well suited for reinforcement learning. And later I will show a mean-field Q-learning algorithm. So in fact, we have a hierarchy of settings in some sense. There is a case where you know the full model. Then you can use, for example, gradient-based methods or exact dynamic programming. There is a setting where you don't know the model, but you observe the evolution of the mean field distribution. So this is a true mean field distribution pushed forward by the environment. So you don't know exactly how it is pushed forward, how it evolves, but you assume you observe it perfectly. And then the next step is to say, well, in practice, we probably never observe the mean field distribution. What we observe is most likely a finite population. So there is an extra layer of approximation. But if you see it in this way, I think it becomes easier to analyze a lot of these algorithms, starting from understanding the exact updates, then doing a model-free version with true mean field, and then the n-agent version. So two algorithms, policy gradient. So policy gradient is similar to what we did in lecture 1. The idea is you have a cost, which depends on the policy. You parameterize this policy using, for example, a neural network, and then you do gradient descent. If you know perfectly the model, then you can do gradient descent, as we did in lecture 4. This was a direct approach for MFC. Now, if you don't know this, what you can do is you try to use your approximation based on the model. So if you know exactly the gradient, you can do this update. If you don't know the model, but you have access to a mean field simulator, meaning a simulator that returns a true mean field distribution, then you can approximate this gradient using, for example, zeroth order optimization techniques. And if you have access to an n-agent population simulator instead of a mean field simulator, then you get an extra error term. And then combining all of these and using techniques that have been developed to analyze policy gradient for linear quadratic problems, we can get a rate of convergence for this one. In fact, the 3 of them, but in particular the last one. And we can show that it converges at a linear rate, at least what is called the linear rate in the optimization literature, which means that you need to take an order of updates, an order of iterations proportional to the log of 1 over epsilon, where epsilon is going to be the bound between j theta k and j theta star, so the optimal ones that you can get. So actually, this is in a paper that has been out for a while, but we haven't submitted it yet. So we will hopefully finish it and submit it this summer. But if you have comments or questions, please let me know in the meantime. Here is, okay, there are some illustrations. Again, it's linear quadratic. We have an analytical solution, so we can compute the true benchmark. And interestingly, we realize that even in dimension 1, even with just 2 agents, you manage to learn a policy which is pretty good. The only case where it fails is when you have only 1 agent. Of course, when you have just 1 agent, at least if you do the naive approach, you don't have access to the mean field. So you are completely off. You behave as if you were alone, but in fact, there is a mean field. But as soon as there are 2 or more agents, you start being able to learn the dependence on this mean field. Actually, there are ways to make this method work even with a single agent using oracle-free, so-called oracle-free methods. So I give the reference a little bit below, but there is a group at UIUC who worked on this. Okay, so here are more plots, and you can see convergence towards the true solution. So trying to learn the mean field solution can be a good idea even if you don't have that many agents. When the state is in higher dimension, things get a little bit worse. But at least in small dimension, having relatively few agents is already a good idea. So, okay, by the way, this answers maybe one of the questions of Abdu. What we do in this plot, maybe I should explain that. So you see that for 1 agent, what I've shown before is 1 agent does not manage to learn the mean field control, the control that is optimal in the mean field regime. But if you take the control learned by this agent and you plug it in the single agent control, then it actually matches the optimal one. And same thing, if you take the control learned by 2 agents, it's not perfect in terms of the mean field problem, but it's actually very good for the 2 agent problem, etc. So taking your agents, asking them to learn the mean field solution is actually a good idea, even if later on you plug the solution in the finite agent problem. Sometimes you get a very good candidate control in this way. All right, so Q-learning now. So the goal is to learn the value function, and that's why we did this dynamic programming principle, right? For policy gradient, we don't need dynamic programming. We directly aim for the minimization of the cost or the maximization of the reward, if you want. So here, I just rewrite the mean field Markov decision process. And the idea is you can introduce a Q function for standard reinforcement learning. So this is standard RL, and this is for, let's say, mean field RL. So the idea is that now you put bars everywhere. So what bars mean? S bar is basically a state distribution. A bar is a state action distribution. And the bar on the pie means that you have a policy at the level of the population from which you sample a policy for all the agents, right? So there is a kind of meta policy for the population, and you sample from it, and you get a policy that each agent can use to then sample their actions. So that's why there are several levels of randomization in this problem. Nevertheless, if you forget these details, you just look at the expression. It looks very much like the standard Q function, except everything is on more complicated spaces somehow. But then there is hope to apply standard Q learning. So here I rewrite the Q learning algorithm. The idea is that the Q function basically solves a fixed point problem. So here, the fixed point is for the operator T star. And the basic idea behind Q learning is just to iterate this operator T star. So T star is called the Bellman operator, and you iterate. So how do you see there is a fixed point operator? Q star is involved here and here. So this is really an equation to solve, and you phrase it as a fixed point equation, which has nothing to do with fixed point for mean-free games. Here it's really fixed point for this function, and you want to find this function. So this is the idea behind Q learning, but in practice, you cannot do perfect updates. In particular, you cannot compute this expectation perfectly. Maybe you cannot even compute the soup perfectly, but even if you assume you can compute the soup, you still need to approximate the expectation. So the real Q learning, what we usually mean by Q learning is at each iteration, you pick one sample, which comes, for example, from a trajectory, and you do one update of Q based on just a sample, which is reminiscent of stochastic gradient descent, but it's really a different idea. Here, you are trying to solve, you are not trying to minimize something, you are trying to solve a fixed point equation. So for the implementation now, if we think about how to implement that concretely in a computer, it's not so simple because, of course, you have this distribution that is here. So if the state space is finite, so let's imagine that S is finite. I will focus on this case, and A is finite as well. A finite. Well, you still have a problem because S bar is really an element of P of S. P of S is finite dimensional, so that's a good news. But it means that you want to learn a function, Q bar, which takes a vector as an input. So this function, I don't know a priori how to represent it. I need some kind of approximation. So one way would be to say, I have a function defined on a finite dimensional space. I will approximate this function using a neural network. This will be the deep reinforcement learning version. The simplest way is to say, I am going to replace, I really want to have a finite, an input which takes a finite number of values. So I replace this by an epsilon net, which is going to be a discretization of the simplex. Okay, so if I replace the simplex by a finite number of points, and if I say my input S bar can only take a finite number of values, and I do the same for A bar, then I have a function Q bar, but approximated, defined only on a finite number of points. And I can have a tabular representation of this Q bar, and I can apply so-called tabular Q learning. Otherwise, if I want to stick to the simplex, the whole simplex, I need to do some kind of function approximation for Q bar. And here I'm going to use neural networks. So I show an example here from Borrow that I already mentioned, particularly when talking about the master equation earlier today. It's an example from Kolokoltsov and Bensoussan of cybersecurity, where you have 4 possible states. So S is definitely finite, but again, P of S is embedded in R4. So it is not finite dimensional. I mean, it is finite dimensional, but it is not finite. So what you can do is you can replace this by a finite number of states. So you discretize the simplex of states and the simplex of actions, and then you obtain a Q bar that you can represent as a table. Why is that? Because you are going to put all the different actions here and all the different mean field here, so state here, S bar, and actions A bar, but you have picked a finite number of them, right? So you need to constrain your system and make sure that the system takes only values in this restricted state space, which you can do by projection, for example. Then you use standard Q-learning from the literature on reinforcement learning, because now it's finite. Everything takes only a finite number of values. And you can play the same thing. You learn the Q function after you learn. So here, the algorithm is going to give you a candidate for Q star. Based on this candidate for Q star, you can recover a candidate for alpha star, the optimal control, or the policy. But here, let's imagine we don't randomize. You get alpha star, and you can plug this in the dynamics. Oops, dynamics. And from this dynamics, you observe this. And you see that the dynamics of the mean field controlled using this learned control, somehow the control you learned by the algorithm, approximately matches the one coming from the ODE. But you see there is some error here, for example, between these 2 lines. So this is M coming from the ODE method for state number 4, which was, I think, undefended and susceptible. And the M coming from the Q-learning is close, but it's not so close. And part of the reason is because we have discretized the space for the distributions. So anyway, it cannot get very close if the ODE is not taking value exactly at one of the states in your finite state space. Same thing for the value function. You can compare the value function learned by Q-learning and the true value function coming from the ODE method. And you see here there is some clear, I would say, a quantization, right? The value jumps between different values and it cannot take any value in between because of the discretization error. So you can take more points. I think for this simulation, I used maybe 10 points in each of the 4 states, meaning that in principle, you have a histogram over 4 states. And now I say the histogram can take only discrete values for each state. But you see 10 to the 4 is already 1,000 points. If you want to put 100 points in each state, it's hard. And if you have more states, it will be also more costly, right? So this method does not really scale up. But the good thing is we understand it well. We can have convergence result for this tabular Q-learning. So that's nice, as a first method. There are more examples. I will skip that. Instead of doing this discretization, we can also put a neural network and train it using, for example, DDPG. So here the idea is I want to take S bar in P of S, which is embedded in R4, and I want to plug this. So I want to plug a vector as an input of my Q function, right? And same thing for the action, my Q function, Q bar. But how can I approximate the Q function? Well, I replace this by a neural network, Q bar, parameterized by theta, which takes then 2 inputs. And then it's not a problem to have continuous inputs taking continuous values. I say it's not a problem, at least you can plug that in the neural networks. And training the neural network is a whole different story. So, right, there are more details, but I want to show just a few plots and maybe one code, and then we can take a break before discussing mean-field games. So here is a code. I will come back to this maybe. Another example. So this is the code really for the example I just discussed, the cybersecurity model. But the code is based on the DDPG, not the tabular Q-learning, which is more restricted. So I'm going to show this code, but before that, I show another application of more or less the same code. So this application is the following. Imagine that you have a finite number of states and you have some initial distribution, maybe something like this, for example, and you have a target distribution, maybe something like this, for example. And your goal is to transport this initial distribution to match the terminal distribution. So it's not going to be, strictly speaking, an optimal transport problem because there is no hard constraint to satisfy this terminal condition, but there is a cost if you don't satisfy it. So your goal as a central planner is to find how to move the particles or the robots so that the final distribution matches the target distribution. The space is discrete, so there is a peculiarity here, which is, if you think about it, imagine that you start, so you want to be able to do that for any initial distribution, right? That's the difficulty. You want to be able to do that for any initial configuration, not a fixed one. Otherwise, the problem becomes much simpler, right? So that's why the value function is a function of the mean field, because we don't know the initial mean field. So you are going to give me an initial state distribution, and starting from here, I have to be able to transport it towards the target distribution. So imagine you give me an initial distribution, which is basically a Dirac, which is concentrated at one state, and I want to match this terminal distribution, which is spread over several states. If there is no noise in the dynamics, there is no way I can do that using pure controls, right? Because all the agents here, I'm going to tell them, go to the right or go to the left, and they're all going to do that, right? And if they all do that, I will always have a mass of one moving to the left or to the right. So if there is noise, it may help, but here I will consider the case without noise in the dynamics. And in this case, the only way you can match any initial distribution to this terminal distribution is by allowing the agents to randomize their actions, right? So here, randomization of actions at the agent level is really necessary. So that's also for this and also for mean-field games, as I'm going to discuss next. That's one of the reasons why I insisted on randomized policies during the first lecture. It's mostly useless for continuous space mean-field games, or at least it's not studied in that setting, not much. But in the discrete case, there are many examples where it's really important to randomize actions. So I just show some results. For example, after training, you are able to match this initial green distribution towards the target distribution, which is given by the blue dots. And so you see that the histogram at terminal time matches these blue dots. And this works even if you start from this distribution, or if you start from some very weird distribution like this, the neural network is able, the control deduced from the neural network is able to transport the distribution towards the target. On the right, this is the action probabilities. So I'm not going to spend too much time on this, but what you can see is that at each state, so for example, let's take this state, the state number 2, you have a certain probability to go to the left. So here the probability is 0. Let me zoom in. You have a certain probability to stay at this state. So here the probability is about 0.5. And you have some probability to go to the right, and the probability is pretty high. So why is that? Because at the beginning, all the agents are on the left. So basically, all the agents want to move to the right with some probability. Maybe you don't want to move extremely quickly. Now, if you look close to the terminal time horizon, you see that for the states which are in the support of the target distribution, all the agents decide to stay and they don't move. Why? Because they're already matching the terminal distribution. So there is no point in moving around. Okay, so maybe it sounds a bit strange if you think about it. This is solved using DDPG, which is deterministic, to learn a deterministic control. So it sounds a bit strange. Why do we use a deterministic method? I mean, a method learning a deterministic policy. But the reason is that it is deterministic at the level of the population, and it is randomized at the agent level. So all the techniques from DeepRL which learn deterministic policies can be useful if you don't need randomization at the population level. Okay, let me show this sample code and then we can maybe take a break, except if you have questions. So feel free to post questions in the chat. I know maybe this is a little bit fast. I'm giving a lot of information, maybe in a short amount of time, because this is the last lecture, and I want to give an idea of the diversity, but yeah, feel free to interrupt me and ask questions. So this is the example for the cybersecurity. And at a high level, what you need is an environment here, and then you need a neural network, and then you need basically the algorithm to train the policy. So this is for the setup. The environment is defined here. So you see here, I define all the parameters. In particular, the betas are given for the transition rates in the transition matrix. You have a function for the running cost, which is the cost of defending or the cost of being infected. This is useful to update the distribution. So all of this here is for the distribution. And the key function is a step function. So if you want to use, this is based on GIM AI environment. And by the way, I should mention that this is based on the implementation of DDPG provided on the website of Keras. So you can go to this, check their implementation of DDPG, and this one is a modification. Okay, so you need this step function, and what the step function does is you give me an action. I am the environment, you give me an action. Based on this action, I move the mean field, I compute the reward, and I give you this information. And I don't tell you how it is computed. So here, you compute the new mu and the reward, and you return that at the end, possibly with some extra common noise. So because you can do the same thing with common noise to make things more spicy. And this is where you see how the reward is computed, and it's really computed for the whole population. So here you could say, wait, I give you one action and you update the whole mean field. How is it possible? This is because one action here is basically a decentralized control function. So it is a function of the state. There is a finite number of states. So basically it will be a vector, one value for each state. And it tells you how the agent should behave in any possible state, right? So one action here is more complicated because it's a mean field MDP and not a standard MDP. I will skip the replay buffers. This is a trick that is used to improve training. Then this is where you see the definition of the actor and the critic. So the actor is basically the policy, and the critic is the value function. And they are going to interact. So this is an example of a DeepRL method where we train simultaneously the actors, the control, and the value, the critic. Here we use neural networks with just a few layers and 100 neurons, but you can play with these architectures. This is to compute the policy. So this is to sample an action from the actor. This is to do the exploration noise. And here, sorry, I should add, this is what I was looking for, actually. We should add the training function. And this is really the function that would be in charge of doing the training. So this is the important function you want to look at, this train policy. You have a loop over episodes. And inside this loop, you keep updating the state. And for each state, then you take an action, you call the environment.step, right? So this is going to do one step. This is the arrow where you give me an action, you give to the environment an action, and the environment returns the new state and the new reward, right? So it's exactly doing this as was described in the small diagram I showed at the beginning. Okay, then there is, this is just for plotting. So there are many lines of code just for plotting. Okay, and then you have the main loop here. I mean, you just call the train policy function and it is going to execute this main loop. And what you see here, so if I go back, I didn't try to tune the parameters in this code. So you can play with it and tune the hyperparameters. But basically, at each iteration, it's going to have several test cases, starting from, for example, 0.5 for all states. And this is the evolution of the mean field given the current actor, meaning the current neural network for the control. And probably this is not the correct solution because for now, the control has not learned anything. This is for another initial state. All the mean field values are at 0 except here, meaning everyone starts in the state defended, infected, etc. So you have, I think, 4 or 5 different test cases. Then the training starts. At each episode or every 10 episodes, we print the reward and the reward increases, right? It is negative, but it's a reward. It increases, not in a monotonic way, but it increases. And then you can keep training in this way. And hopefully at the end, you get something that is better than at the beginning. Here the reward has increased a little bit, but I'm sure it's possible to do much better with more iterations and maybe a smaller learning rate. Are there any questions at this point? That's about what I wanted to say for mean field control, and then we move on to mean field games. Any questions or comments?
Yes, there is one question in the chat.
Thank you. Yes, could you show some real-world examples? Well, so everything is real-world in some sense. Everything is real, but I assume you mean maybe some applications like maybe industrial applications. I don't have any really industrial applications at a very large scale and solving a real problem. So I think that's one of the objectives. Next step for mean field games would be to solve some real like industrial applications. So it's true. Most of what I'm presenting here, sorry, is quite a toy model. I'm going to show later on one example which has a lot of states, which is an evacuation from a building, but it's still a very stylized model. So it depends. If you want some real-world motivations, I have plenty. If you want a real-world application that has been solved or improved using mean field games, this I'm not really aware of that. I know that Lyons and Lazary and co-authors have worked on, for example, telecommunications, maybe also advertisements. So I'm not sure exactly if it has been put in production, you know, to the point where you can really develop it in a company. But there are several papers discussing motivations in terms of applications. Yeah, so I can send you some references if you want later on.
And there are also some people from EDF who are working on on electricity consumption and production.
Yes, indeed, yes. Like Clément Salasser and Xavier Varin and collaborators. So yes, indeed, electricity management is also a good point. Okay, so if there are no further questions, maybe we just take a few minutes break before I move on to mean field games, if it's okay for you.
Yes, Mathieu. Okay, so we restart at 3:40 here in France. So this should be 2:40 in Morocco. So this is fine to everyone. Okay, so in 8 minutes.
In 8 minutes, yes. Okay, sounds good. Perfect.
So 3:50. What I said.
Yeah,
50. Sorry,
50.
I 40. Yeah, sorry. 50.
No problem.
50, 250 in Morocco, 350 in France.
Great. Thank you. See you soon. All right, so maybe we can start. So what we did in this first part of lecture 6 was to introduce reinforcement learning and then recast mean field control problems in discrete time as a mean field MDP, which is just an MDP of a special type, and then applying standard reinforcement learning methods, more or less standard, tabular Q-learning or deep reinforcement learning to this mean field MDP. So let me move on to mean field games. The setting, in fact, the setting, we have already discussed almost everything. So now it's more about recombining ingredients we have already discussed. So as I said, there will be a meta level and then a lower level where we do reinforcement learning. So the setting, first of all, I start, sorry, with a few remarks about learning. So learning has many interpretations, and there are at least two popular interpretations which are not incompatible and somehow, exaggerating a little bit. But one interpretation, very common in game theory, in particular algorithmic game theory and evolutionary game theory and economics, is about iterating. So how you update the policy step after step until maybe it converges to an equilibrium, or maybe you are interested in some non-stationary behavior and you look at the evolution of the policy. And the other interpretation is more in machine learning. You pick some samples, you try to do some experiments, and based on the experiments, you get some information, you improve your behavior, and then you repeat like this. So really using samples and experiments. And somehow what we are going to do here is combine the two. We are going to have learning at the level of the population. So it will be like a dynamical system at the level of the population. But the way you update the policy inside is using reinforcement learning. So what did we see before in terms of learning and optimization methods, fixed point, honor, mirror, descent, and variations? And so actually, this is studied a lot in games. So finite player games or infinite player games in economics, non-atomic games, and also mean field games in particular. I think starting with the PhD of Hadi Kanlu, at least as far as fictitious play is concerned, fixed point iterations were already used before. So the generic structure will be the following. At each iteration, say K, you have a current policy. You deduce what happens if everyone uses this policy, and then you update by computing, for example, a best response. In fact, it doesn't have to be that strict, as I described here. Maybe you can do some averaging along the way. Maybe you can do a greedy policy instead of taking a best response, or something like this. So there are many variations. But the idea is you iteratively update pi k, mu k, pi k plus 1, mu k plus 1, etc. So this is what I would call the meta algorithm. The question is, how do you do these updates? And then along the way, there will be this particular step, which is how to compute the new policy. And this, you can do it, for example, using reinforcement learning methods. So two types of learning, the outer loop and the inner loop. Okay, so we are going to need this best response map to define the fixed point iterations. I already defined actually this best response map. So it is the argmax. In general, the argmax is not unique. So you may need to decide which policy you want in this set of argmax policies. And same thing for the population behavior. I already defined it before. Maybe I denoted it MF instead of PB. So I will use different notations, but basically it means you update the mean field based on the current policy. So for example, you start from an initial distribution and then you push forward using the policy. And a mean field Nash equilibrium is a fixed point of this. Notice that in some cases you have a unique fixed point in terms of mu, but maybe pi hat is not unique, right? You could have many policies that give you the same distribution. Sometimes you have the same state distribution. So there are many pitfalls, but usually we make assumptions to avoid these problems. Okay, I just want to mention that the world is bigger than the setting under which we usually work. So here I will just summarize several learning optimization methods. So this will be the meta-learning part, so the meta-algorithm at the somehow at the level of the population. First one, fixed point method, or Banach-Picard fixed point, if you want, because it's based on this Banach-Picard fixed point theorem. So you have mu k, you compute pi k plus 1 by taking a best response, and then you get the mean field flow associated to pi k plus 1, assuming everyone uses this policy, right? And you are hoping that this is a strict contraction. So if you take a specific model and you do the computation to try to see if it is a strict contraction, you will realize that typically it relies on having the model, functions of the model, in particular the drift or the transition kernel and the reward, which should be Lipschitz with respect to the mean field and with small enough Lipschitz constant in order to have a strict contraction. So you can check, for example, this paper, and one way to improve that is to relax the problem. There are different ways to relax. One way that has been studied is by adding an extra term in the reward function, an entropy term, which forces the policy to be diverse. So it cannot be concentrated on just one action because you penalize depending on the entropy of the policy. So the policy is the distribution over actions. If you penalize based on the entropy of this policy, it means you force the policy to diversify the actions. And this regularizes, in fact, the whole process here. So you still do these fixed point iterations, but with a modified reward and hence a modified best response function. And this can help to get the strict contraction property. Of course, the drawback is that because of the entropy regularization that you add in the reward function, you are not solving the original game, right? So you tweak the reward function, then the problems become more solvable, but it's not the original problem, right? So there might be a gap between the two. Okay, so there are many variants, in particular fictitious play. So fictitious play, here I present it as a modification where at each iteration you compute this average mean field, and then you plug the average mean field here. Actually, there are different ways to view that. Maybe it would be better to average policies and then deduce the mean field generated by this average policy, right? So here, other idea, average policies. Because in fact, when you look at finite player games, very often what people do is average policies rather than the state distribution. So you average policies and then you deduce the state distribution that is induced by these average policies. So something to keep in mind, but in some cases it's equivalent. So convergence typically holds under Lazarus monotonicity. I already mentioned that, but here I add a small information, which is that in fact what the Lazarus monotonicity brings is that you can use the exploitability as a Lyapunov function for the evolution of the algorithm. And using this Lyapunov function, you get convergence. So what is the exploitability? The exploitability is basically how much you can be better off by deviating. So imagine that you are given a policy pi. You can say, I play pi, and the rest of the population plays pi. So I get mu pi, mu generated by pi. But I can compare that with what happens if everyone still plays according to pi, but I play according to some pi prime. And maybe I try to maximize my reward if j is a reward. if I can be, if this quantity is very positive, it means I can be much better off by deviating. So pi is not a Nash equilibrium, and this quantity is equal to 0 if and only if pi is a Nash equilibrium. So in fact, we can use that also numerically to assess the convergence of the algorithm. If this quantity goes to 0, we have a Nash equilibrium. Because in principle, it's not easy to check whether what you have is a Nash equilibrium, right? Because remember, fixed point problem is not optimization. So how do you check if you have converged to a Nash equilibrium? Well, this is one quantity that you can use to check, because you know that it has to go to 0. So I'm going to show some experiments. In the experiments I'm going to show, we are using the exploitability. One drawback of this quantity is that you have to compute the sup over pi prime, so it is costly, right? In general, you don't know what is the best policy, but this is basically computing a best response. So if you are able to compute the best response at this stage, then you are also able to compute this sup, right? It's just that it might be a bit costly, and maybe it's an approximate best response and not a true best response, but you can estimate the exploitability. So this is for fictitious play. I already discussed it before. Here I give some extra references. So if you want to see this proof, I think it's actually, yes, I think it's actually in this paper. If you want to see the proof of convergence based on the Lyapunov point of view for a continuous time version of fictitious play, meaning the updates are done in continuous time. So if I take one step back, this fixed point method is more or less equivalent to a value iteration. The idea of value iteration is that at each step, you compute an optimal policy, and then you you just repeat like this. Or if you do it in a stationary, actually usually it's done in a for stationary reinforcement learning problem. In this case, what you do is you compute a greedy policy. Sorry, you really compute an optimal policy at each iteration. So this can be quite costly. So what I mean is here, let me just refer to this. What I mean here is you solve a best response, you compute a best response, which means fully solving the MDP. And this would be costly, right? So mu k is given, and you have to solve the MDP to get the best response. Maybe it's not necessary to do that. Maybe it's enough to do just one greedy improvement and then keep iterating by doing greedy improvement. And that's the idea behind policy iteration, which is the standard method for usual reinforcement learning for a single agent. Here, it has been adapted to mean-field games. Of course, the challenge is you have to intertwine the evolution, I mean, this value iteration or policy iteration update with the update of the mean field. Right, so here we have to alternate these two, and same thing in policy iteration. We are going to need to intertwine the evolution of the policy and the evolution of the population. So here is policy iteration written with a Q function. The idea is that at each iteration, you have a candidate policy in mind and you have a candidate mean field in mind. Given this, you evaluate the Q function. So this is somehow the standard Q function for the agent, the representative agent facing this mean field. You get a new Q function. From here, you take a greedy policy. So greedy means that you just take the optimal action at each x. So here somehow this step is for free because you have the Q function, you just computed it. And then what you do is for each x, you look at the best action. So at least if you have a finite number of actions, it's just going through the actions one by one and picking the best one. But there is no MDP to solve. When I say for free, it's not true. You have to find the best action, but it's just an optimization problem, not a full MDP to solve. And then you update the population based on this policy. So in fact, this method, here I describe it using Q functions, but it has also been studied in the continuous setting, continuous time, continuous space, in particular by Kakache and Camilli and co-authors Qingtong and etc., and also by Cui and couple in a reinforcement learning setting. Here again, this is a kind of exact update version, and now you can introduce a smoothed version as we did, starting from fixed point to fictitious play. We can go from policy iteration to a smooth version, and there are different ways to do the smoothing. One of them gives you what we called here the online mirror descent algorithm. So the idea of the online mirror descent algorithm is that when you take the optimal action, you don't take it with respect to the Q function you just computed, but somehow you do an averaging, or rather a sum, over the Q functions. So you see here it is a sum with a discount, eta, I mean a multiplicative factor, eta. So you sum the Q functions, and then you use that to compute the argmax. I mean, you base your argmax on this. So intuitively, this is going to slow down the iterations, accumulate information, and implicitly regularize the algorithm. Furthermore, gamma here is not a pure argmax. Typically, it's a regularized version. So for example, it can be a softmax. So softmax is going to give you a distribution pi over actions, and the weights, the probabilities are higher for actions with a larger Q value, and the probabilities are smaller for actions with a smaller value, but it's not something that is concentrated on the best action. It's something that is really distributed over all the actions, and this will also help to make the process smoother. So what happens is, so you could say, well, how is this going to converge? Because next I claim that we have convergence. So how is this going to converge if you have a softmax? Because the softmax here is going to force the policy to take actions everywhere. So you could say this is never going to converge to a policy which is concentrated on the optimal actions, because not all actions are optimal. In general, you have a subset of actions that are optimal. So in fact, what happens is that because of this sum here, which is a sum and not an average, there are some values. So Q bar K plus 1 at X and A is going to go to minus infinity, I think, if we are maximizing. So this is going to go to minus infinity for some A's. So for some actions, the Q value is going to go to 0, to minus infinity. And if it goes to minus infinity, the softmax at this point is going to converge to 0 in the limit. Okay, so here is what I wanted to say for the meta algorithms. Typically convergence again, and there is this monotonicity structure. And here is a summary. Starting from fixed point iteration, you can define fictitious play by averaging the mean field or averaging the policy. Starting from policy iteration, you can get online mirror descent or smooth policy iteration using a sum over the Q functions. Actually, this one is online mirror descent, and there is a recent paper by Qingtong and co-author where they do smooth policy iteration. But in spirit, you start from policy iteration and you smooth the updates to make the convergence more more certain, or at least under less restrictive assumptions. There are other ways to regularize. So I mentioned the averages over past iterations. I mentioned the argmax that you can transform into a softmax with a certain temperature here. And you can also regularize the reward by adding an entropy term. For example, the log of pi versus pi tilde being a reference policy that you have in mind, maybe uniform, maybe not uniform. It could be the pi coming from the previous iteration. So there are many ways to play with these variations. I think it's helpful to start with the simplest algorithm and then see, add bells and whistles and see that as a kind of regularization. I think it also helps for the analysis. So there is a question, thank you. So bar Q is a kind of momentum, yes, that builds up with a very small eta, yes, in the same spirit of Adam. In some sense, yes, you can say that because you are really summing the Q bar. But as I said, part of Q bar is going to go to infinity, right, or minus infinity. And this is important for the convergence in the limit. But numerically, maybe at some point you let eta decay to 0, or you can take a dynamically changing eta. But here I take a fixed value. And numerically, I mean, you really need to play with this eta. There are some cases for which numerically, with a small eta it works and the big eta it doesn't work, or vice versa. I mean, there are different situations. So eta is an hyperparameter, and I think you need to do experiments to figure out the value. All right, so now reinforcement learning. This is somehow the lower level learning at the level of the agent. We can use basically any reinforcement learning algorithm from the literature because mu is given to you and you update by doing a reinforcement learning method. Okay, thank you for your question. So here I don't have anything to say. I will just show some examples. So this is, again, the systemic risk model that I described in the previous lecture with common noise, but here we take a discrete time model, and also we assume that the common noise can take only a few values, for example, +1, 0, and -1. So this is a very restricted form. It's not a good approximation of the continuous model, not really. And so we can solve this model using backward induction and fixed point or fictitious play, and we can also solve it using tabular Q-learning combined with fictitious play. So the meta algorithm is fictitious play, and at the reinforcement learning level, at the agent level, we use tabular Q-learning, and we see that the exploitability is decreasing. If you use backward induction, in the sense you really use the model to do the backward induction, it converges faster than if you use reinforcement learning, because there are some errors, and so it takes a while to decrease the exploitability. This is another model. So here we revisit the model of Almula Ferreira Gomez, the ergodic one, which has an explicit solution. This one is in continuous space, and so we solved it using fictitious play and DDPG because we wanted to have a method that works in continuous spaces. So we have to learn a control that can take any input between 0 and 1 without discretizing. Another example, this time in continuous space, but in higher dimension 3 plus 3, right? Because we have 3 for X and 3 for V. So it's a 6-dimensional, the state is in dimension 6, and the control, the acceleration is in dimension 3, right? So the dimension here is pretty high, in particular approximating the distribution in dimension 6. It would be difficult with an empirical distribution. As you can see here, the birds are pretty spread. So if you use an empirical distribution, you are not going to get a good approximation. So what we do is we use a neural network to learn the distribution, in fact. And here we use normalizing flows, which are a class of neural networks designed to approximate probability densities. Then it is in continuous space. We don't use tabular reinforcement learning. We use, again, a deep reinforcement learning algorithm. And this time we use soft actor critic to learn the policy. And at the end, you see the birds that align. I think I've already shown that actually in the first lecture, right? I've shown the video and the picture. So it was based on this, this method. Another example, so I was mentioning building evacuation when I was asked about real examples. In this paper, you have a kind of realistic example based on an experiment for the evacuation of a tower. I think it's a Burj Khalifa, which has, I don't know how many floors and how many people, but a large number of people, large number of floors. And so for this type of building, it's really important to do simulations about how people can evacuate, where to put the exits, where to put the elevators, etc., or the staircase. So here we are not taking a very realistic geometry, but the motivation is the same. You have several floors, you have people at different floors, and they pay a cost or they get a negative reward when they are at a high floor. So you get a high reward if you are at floor 0, and otherwise you don't get this reward. And also you pay a cost if you are in a crowded region. So you want to avoid the crowd. So Julien Perola did this simulation. I think it has maybe 1 trillion states or something like this. So he discretized with a very, very fine mesh. And then here you need a lot of GPUs to do the simulation. It's somehow just to see if the method scales in terms of number of states. And at least on our online mirror descent does, and you can see the exploitability decreasing. This is for online mirror descent. In blue, in red, it is for fictitious play, and in green, it is, fixed point damped with 10 to the -5 and fixed point damped with 10 to the -3. Here I'm extrapolating a little bit, so let me erase this. But basically, OMD seems to converge faster than damped fixed point, at least on this example. Another one that I showed in the first lecture, so hopefully now it makes more sense. This is the example with 4 connected rooms. People start in the top left corner and they pay a cost, which is the entropy. So they want to minimize entropy by spreading throughout the room. Okay, so how do you, what do you see here is, what you see is a result for different algorithms. So actually we try a bunch of algorithms, fixed point. You see that the terminal distribution is pretty bad, it doesn't work. Fictitious play, the distribution is pretty uniform. OMD, damped fixed point here didn't work. Policy iteration, fictitious play with a softmax policy, and fixed point with a softmax policy. So here, fictitious play and OMD seem to be the best. And if you look at the curves of exploitabilities, you see that indeed the ones that work the best are the orange one and the blue one, which are for online mirror descent and fictitious play. The good news is you can reproduce this experiment in just a few lines of code. And how? Using OpenSpiel. So I still have a little bit of time, so I can mention that briefly. And so in OpenSpiel, you have this environment, so the game, and you have the algorithms. At least most of them here are implemented or can be obtained with a very simple modification. So I'm going to show that briefly. A slightly bigger experiment with a maze. And this one is solved using deep reinforcement learning. So we wrote a version of online mirror descent and a version of fictitious play where the updates of the Q function. So for online mirror descent, we need to update the Q function. Here we need to update the policy by computing a best response. And each of these can be done using deep reinforcement learning. For example, this can be done using DQN, and this can be done using other algorithms to compute the policy, or DQN as well, in fact, and then you get the policy from here. And that same thing, this one is in OpenSpiel. Maybe I will skip this section. This is a section to say that actually mean-field game and mean-field control are not completely disconnected. And you can write intuitively, the idea is in both of them, you can approximate the solution of a mean-field game and the solution of a mean-field control problem by updating the population and the control, but updating at different rates. If you update slowly the population and quickly the control, intuitively you are doing a mean-field game. If you update very quickly the population and slowly the control, basically you are solving a mean-field control problem. So that's the intuition behind this 2-time scale approach that we developed with Andrea and Julie and Jean-Pierre Fouque. And we are still working on the proof also with a PhD student of Jean-Pierre, Meng-Jouet. And so we don't have the full proof of convergence. So the story is not as simple as this. Okay, this is kind of the ideal story that we get min-field control on min-field game. When you look at the details, it's a bit more complicated, but intuitively you have a single algorithm which can do min-field game or min-field control depending on how you tune the learning rates. So I will skip these. There are several follow-ups, and here is a work I mentioned with where you don't need the distribution at all, and the agent learns the distribution along the way, which is also actually what we are doing in this setting. We are learning the distribution along the way. So I don't know if there are questions. Otherwise, I want to say a few words about OpenSpiel. In fact, you can find tutorials online. So what I would like to do is describe min-field games in OpenSpiel and not all of OpenSpiel. So OpenSpiel is an open source framework for research and for multi-agent learning. So it was developed by Mark Langto at Google DeepMind, and then several other contributors, more and more contributors, in C++ and Python. And it covers many games, including chess, blackjack, Atari, poker, Go, and others. So for example, you can see the algorithm used for AlphaGo and even for AlphaZero. It's implemented in this library, right? So you can take a look at the code. It's open source. Of course, if you want to run it, maybe you need a few hundred of GPUs for a few months if you want to get the same performance. But I'm exaggerating a little bit, but okay, it doesn't mean you can reproduce exactly the experiments that are in the paper of AlphaGo, but you can see the environment and the algorithm. And also recently, min-field games. So the idea is really to have a common framework where people can contribute, can bring their algorithm. Everyone can test all the algorithms on different games and see the performance. And then everyone can benefit because we can all understand how such and such algorithm behaves on such and such games. And there is not one algorithm which is going to be better than all the other algorithms all the time. So this will help to somehow provide a common framework. The price to pay is, of course, you have to get into this library and understand the logic. So let me try to explain. First of all, there is a documentation. There is a Python notebook to explain the basics of OpenSpiel for general games, which cover games with partial information and very complicated structures. And we don't need all of that for min-field games. It will be in some sense simpler. Very nice tutorial by Mark Langto, and also a paper. So there are two main components to understand how to define a game and how to define an algorithm. Min-field games in OpenSpiel, so really the main contributors, Julien Perola and Raphaël Marinier, Satan Gergin, and then a growing number of contributors, including Théophile Caban, Sarah Perrin, and Paul Muller, who worked on some algorithms and environments. So how to define an MFG model and how to define a new algorithm. So there are already several examples. So maybe the best thing is you can take a look at these examples, including crowd modeling in 2 dimensions, as I was saying, dynamic routing, linear quadratic, and predator-prey, which is a multi-population example. There are several algorithms, including some algorithms without reinforcement learning. So I think that these ones and this one are without RL, and this one and this one have deep reinforcement learning inside. And you can then define many variants based on this. So you can look at the code and modify it. The main notion to check convergence is exploitability. Okay, and there is more to come soon. And if you want to contribute, that would be great. So the main thing to have in mind is that every change in the game occurs through a node. So everything will be characterized by a node. So in particular, the representative player, when he plays an action, it is a node. When the min-field moves, it's a node. And when the noise acts on the dynamics, noise perturbs the dynamics, it's also a node. So in some sense, the noise is like a player acting on the dynamics, but it's not optimizing any policy. It's not an adversarial noise. It's just the noise in the dynamics. Time is part of the state, so that's something to keep in mind. Somehow the state is t and x. Okay, I'm running short on time, so maybe I will go briefly over this. You can take a look at this. You can take a look at the description of the chance node, player node, and mean field node. One key object is distribution. So here I give several aspects of how the distribution is represented in OpenSpiel. And here is an example. So I suggest that you take the example of crowd modeling, which is in 1D, not in 2D. And here I describe the main classes and the main functions in these classes. How to define a new algorithm? Well, probably the simplest one is to look at the fixed point. And based on that, you can understand the logic. Slightly more complicated is fictitious play. Why is it more complicated? Because you need to merge the previous policy and the current policy. So fictitious play, as we do it here, is actually merging policies and not merging merging the mean field. If you want to do reinforcement learning, you can start with the DQN. In particular, you can look at this folder, examples, which contain several examples with comments, etc. Okay, I have one sample code. I can briefly show it, and then I am basically done. So maybe I can take, I don't see any question in the chat, so I will just show this code, but feel free to post your questions, and I will be happy to answer. So let me show you here the sample code. So if you look at this, you are going to see, I'm not going to go through the details, but you can install OpenSpiel in a notebook, or you can install it locally through pip. So you just use this command and you can install OpenSpiel. So this is really nice. Just in a few minutes, you install the OpenSpiel library. You don't need to go from the source. There are some updates from time to time, so sometimes you need to upgrade. Some imports, then it explains how to create a game, how to generate a trajectory, how to compute the exploitability. So if we click here, how to compute the exploitability, you have a function nashconv, and this function nashconv computes the exploitability, right? So you don't need to implement anything. Computing the distribution, computing the value of a uniform policy, etc. Running an algorithm, well, you call the class or an instance of the class fictitious play, and then you do fp.iteration, and it does an iteration of fictitious play. So really, once you have these algorithms, then you can use them, and any game implemented in this framework, you can test your algorithm. And vice versa, if you design a new game environment, you can test it with any of the existing algorithms with just a few lines of code. And here you can see the policy as a nashconv. So nashconv is equivalent to the exploitability. The nashconv decreases. So it seems that here fictitious play is converging, and you can do a non-linear descent. Same thing, it's just one line of code. I mean, just you call md.iteration, and it does one iteration of online mirror descent, even if your game is very, very complicated, right? As long as the game is implemented, even if it's complicated, mirror descent will do one iteration. You can check the page for OpenSpiel. So here is a list of games, and you can see there are many games that are implemented, and also a few meaningful games among them. And you can go to the GitHub and explore the GitHub. So that's why I gave the link in the slides. You can easily go through OpenSpiel. Then you look at Python. Maybe you want to avoid C++, except if you like C++. Then you have a class MFG. You go here, and you have algorithms, games, and examples. So let me just finish the slides. I know it was very short, but hopefully you can take a look at the documentation later. So what we did today, background and reinforcement learning. Reinforcement learning for MFC, basically rephrasing this as a mean field MDP, and then adapting the reinforcement learning to this strange MDP or this peculiar MDP. Whereas for me-field game, you need to design the meta algorithm, like fictitious play, for example, and inside you plug a reinforcement learning algorithm, tabular Q-learning, DQN, SAC, DDPG, whatever you like. OpenSpiel, there is a survey which is going to be updated soon. If you have comments or questions, that would be great. So I think I'm right on time, but maybe I can take just 1 minute to summarize the course. Let's see. So if we take one step back, lecture 1 was, in particular, if you missed some of the lectures, in case you want to see them later. So lecture 1 was about introduction, and I spent some time defining the optimality condition. So I know that I got some questions after that. So you can check the derivation of optimality conditions. I didn't go too much into the details, but I try to provide the main ideas. And in particular, I spent some time introducing the discrete time, discrete space setting because it is useful for this reinforcement learning literature. Lecture 2 was the case of linear quadratic problem that we approached using ODEs, and we illustrated some of these algorithms, right? So we can already describe why it works. I mean, sometimes it works, sometimes it doesn't work, this fixed point method, fictitious play, etc., using ODEs. Lecture 3 was about the PDE system and how to use finite differences or semi-Lagrangian scheme, as well as the forward-backward SDE system. So I described 2 methods for each of them. One of the issues of these methods is that they don't work very well in high dimension. So then we moved on to deep learning. So I started with deep learning for MFC, the so-called direct approach. And then we did Makin-Vlasov FBSDs. Lecture 5. So this was this morning, probably very fresh in your memory, but still. It was about deep learning for PDEs. So again, it's not at all exhaustive for the literature, but in particular, the MFG PDE system, but also the master equation, at least in some cases. So this is very preliminary, but finite state master equation, for example. And lecture 6, this was today, I mean, this was right now, so reinforcement learning. So I hope this gives you an overview of some of the existing methods. Again, I have some slides where I summarize other references that I haven't covered. I'm sorry if I forgot some references. Feel free to email me if I forgot your paper. I will be happy to include it. Oops, sorry. And otherwise, I will just remind that here are some references about in-field games, some monographs, in particular the book of René Carmona and François Delarue contain really a lot of details about the probabilistic approach, but also about PDEs, and then some surveys. So it turns out I have contributed to some of them because I'm quite interested in this topic, but again, there are many other references in the literature that are also very relevant. So thank you very much for your attention, for the organization. And if you have questions, I don't know if we still have time for questions, and otherwise by email, feel free to reach out at any point.
Yes, Mathieu, we have time. First thing is, thanks a lot. This was wonderful. I think that all of us really appreciated what you have done, and this is absolutely exceptional. And I guess that this will be very useful for all of us. You have one question in the chat, in fact,
yes.
about the extension of the RL algorithms to models with jumps.
Yes. So RL algorithm with jumps, I would say if you are in discrete time, somehow the jumps are there by default. I mean, okay, if you are in discrete time, yes, in discrete time and discrete space, you jump by definition of the model. If you are in continuous time and discrete space, you also jump somehow by definition. So maybe you are thinking about continuous time and continuous space models. There are a few papers on reinforcement learning for continuous time and continuous space, but it's not very common. I can cite some work by Ziad Kobesi, by Yan Pham also. but as far as I know, without jumps. So I don't know if there is any paper doing reinforcement learning for continuous time, continuous space, and with jumps. So this I'm sorry, but if you are taking discrete time and discrete space, there is jump by definition in the model.
Yeah, thank you. Any other questions online? Just one question for you, Mathieu. In these two-scale models that you mentioned, you said that you could have either MFC or MFG in the limits. Could you have some mixture of the two of them as we studied the two of us?
Yeah, I think that could happen. Actually, the story is not so here's the way I present it, and the intuition is that indeed when the learning rate for one is bigger, you converge to MFC, and otherwise you converge to MFG. It's not as simple as just this inequality. So actually, Andrea spent a lot of time doing the experiments to get the plot. And we really needed to tune the learning rates a lot in order to get the mean field gain and mean field control. And when we didn't have the right learning rates, the algorithm still apparently converges, but not to the mean field gain and mean field control. So it seems that maybe the algorithm converges to something in between, but we haven't characterized it. So
you don't think that this could be a kind of interpolation as we studied with René and Gaucher?
Yeah, I think that's a good guess. I don't have a rigorous answer, but I think that's a good guess for the limit, maybe. There is another aspect, which is that the experiments we did, so here I didn't show the plot, but we really recover in the linear quadratic case, again, a solution of mean field gain, a solution of mean field control for some choices of rho Q and rho mu. So it's not for any choice satisfying these inequalities, it's for some choice. And one difficulty was here we were doing the reinforcement learning version, meaning we don't know the distribution, we don't know the reward, etc. So there are a lot of errors that accumulate, and I think this is maybe one reason why the algorithm was not converging to the correct limit. But maybe even if you do exact updates, the algorithm still does not converge to the mean field control and mean field gain, something in between. But at this point, I am not completely sure. Implicit, I mean, when we look at the 2 timescale proof, there are some conditions which are of the type of, I would say, Robbins-Monroe condition, or maybe conditions that are classical in stochastic approximation, which are quite general. So you need some relation between the 2 rates. But in principle, for the proof, as soon as you satisfy this condition, you have convergence to mean field gain or mean field control. So it seems that it's quite general, but in practice, it was not so easy to find the rate. So I'm not sure if it's due to numerical errors or if it's due to something really happening in the region in between.
Thank you. There is another question in the chat by Amatouche. Did you use the dynamical Markov method in reinforcement? So this is at 436 that you have this question.
Thank you. So actually, I'm not sure. Okay, I'm sorry. I don't know this method of the dynamical Markov method. So I'm not sure if I used it or not. But maybe we can discuss afterwards if you can describe it to me, or maybe send me a reference and I can see. I'm sorry, I'm not familiar with this terminology.
Any further question online?
Yes, thank you.
Plenty of them.
Plenty, yes, plenty. So in MFG in general, yes, there are many questions. Maybe just for numerical methods, I have tried to point at some questions. So in particular for this last part, when we discuss machine learning, I think for most of the algorithms that exist, for example, if you want one question, prove a bound on the generalization error of some method. Take basically any deep learning method or reinforcement learning method for these mean field gains, mean field control. And one goal can be try to prove a bound on the generalization error, meaning you really take into account everything, the approximation due to the neural network, the statistical learning error due to the number of samples, and the convergence of the algorithm. So how many steps, how many iterations of algorithm you need. I think this would be beautiful because then you have a full analysis of the algorithm with a rate of convergence. So that would be really great. But as far as I know, this has not been done. Then there are many questions, even for the classical methods. The finite difference scheme, for example, has been analyzed for some setting, like the one I presented. But if you are thinking about non-smooth coefficients, if you are thinking about controlled volatility, etc., etc., there are many directions in which you can try to extend these theoretical results.
Thank you. Maybe we can take one last question.
Okay.
Nassareddin at 440.
Yes. So for MDP, can we use deep learning and neural network to find a general approximation of the optimal policy without trying to find all the optimal policies for the problem? So if I understand your question, it's about what happens when you have several optimal policies. And maybe the question is which one is going to be selected by the neural network. So in any case, yes, deep learning and neural network can be combined. So for example, let me backtrack. I'm sorry, I know it was very fast, but if you look at this piece of code, it's really based on deep reinforcement learning for the MDP for mean field control. So this is really deep RL, and it does learn one optimal policy. I don't think there are multiple optimal policies in this one. The problem is more serious for mean field games. Maybe the question is even more relevant for mean field games. So sorry, if I go here, for example, you see that here there is an issue which is hidden. So very often we describe the method in these terms, but here I write pi k plus 1 belongs to BR. So you can say you are going to use deep RL to compute this best response. Sure, that's fine, but the problem is this best response set, and I think that was one of the exercises maybe in the first lecture, this best response set could contain many best responses, and all of them are optimal, but only one of them will allow you to recover the mu, which is the fixed point, right? So maybe there is a distribution which is a fixed point. Against this distribution, there are many optimal policies, and only one of them gives you the correct mu. And in that case, it's not clear that your deep RL algorithm will select the correct optimal policy, right? And you need to find a fixed point. So fictitious play is one way to fix this problem. Fictitious play learns a randomized policy along the way by averaging over many policies, and in that way manages to select the correct optimal policy among the set of best responses. But it's not a trivial result. It's something you don't see when you have a unique best response. So when you study fictitious play in continuous space, continuous time, making the assumption you have a unique best response, there is no issue. But when you have multiple best responses, fictitious play is even more interesting than in the other case. So you need a combination of fictitious play and deep reinforcement learning, for instance, or at least, I don't know if you need it, but it is helpful in this situation.
Thank you, Mathieu. One last chance for one last question. Nothing on the chat. So now maybe this is time for me to thank Professor Abderrahman Abal, who has been doing a lot for this program for
yes, thank you very much.
3 or 4 years. I don't know exactly when you started this program, Abdou, but this is absolutely wonderful. Also, what you are doing